Today we are going to work on determining limits from graphs. And so what we're going to do is first do a quick recap of our last video. So suppose you were to graph this function, x cubed minus 8 over x minus 2, and x does not equal 2, which is good because if our x equaled 2, this function would have a 0 in the denominator and be undefined. So unfortunately we can't look directly at 2, but that's where the idea of a limit comes in handy. So as our x values approach 2, we use a limit to determine what our y values seem to be approaching. And you don't look directly at 2 because it's undefined, but you can look at really close to 2 or infinitely close to 2. To do that, we're going to use our graphing calculator, and we're going to, after we plug this function into our y equals screen, use our table to determine what we think our function is approaching as our x value approaches 2. So as we pick numbers that are closer and closer to 2, but slightly less than 2, so from the left-hand side, and then slightly larger than 2 from the right-hand side, what happens to our function as our x values approach 2. To do that though, first I said you had to go to your y equals screen and you have to plug in this equation. Make sure you put the numerator and the denominator in parentheses. So there's our x cubed minus 8 on top and parentheses divided by x minus 2 on the bottom, also in parentheses. And again, if we want to look at our table, but we don't want our table to just like come up with every option for us. We want to ask it very particular numbers. So I'm going to go to my table set, which is right here. And then I'm going to go down to independent variable because I want to ask my calculator to do very specific independent variables, very specific x values. And now I can go back to my table. And so now I can go ahead and just plug these numbers straight in. So we got 1.75, 1.9, 1.99, and then 1.999. And these are pretty good numbers to be choosing just because they're very close to 2. I can also try 2 just on its own, and then 2.001, 2.01, 2.1, and 2.25. If you have a graphing calculator, this is a great way to try and determine what a limit is. And so then I can go ahead and fill out those numbers on my paper, so that way I can kind of see what pattern happens. So 10.563, 11.41, that's a little messy, isn't it? 0.41, 11.94, 11.994, and then 2 we had an error, so I'm going to go ahead and just put a big X through there, and then 12.006, 12.06, and hopefully we can kind of see what's happening here. So as our x values get closer and closer to 2, what does it look like our y values get closer and closer to? Hopefully, as you're saying this, they look like they get closer and closer to the number 12. And so then we would say that the limit of f of x as x approaches 2 is 12, and you can write it either this way or this way. I prefer this first version just because it's less writing and mathematicians are lazy. So if they tell you that this equation is f of x, then you can use f of x in your actual limit. So the limit of f of x as x approaches 2 is 12. The informal definition of a limit, and that's kind of what we've been using, is what is happening to y, or f of x, as x gets close to a certain number. And in order for a limit to exist, we talked about this a little bit previously, they have to approach the same y value from the left-hand side and from the right-hand side. So remember, when we did the left-hand side, we use this little negative in the exponent to determine a left-hand limit. So as you come in from the left-hand side, what does your function seem to be approaching? And then the right-hand side has a little plus. In order for a limit to exist, your left-hand limit must equal your right-hand limit, and then we would say that that limit is some number L, so number L here. I'm going to just go ahead and do a bunch of examples, so work your way through these with me, and then we will give you some time to practice as well on your own. So in this first example, so we just have this graph, and we're approaching, it looks like we're approaching 1 from the left-hand side, the right-hand side, the general limit, and then we're actually just going to find my actual value of my function at 1. So I'm just going to follow my graph, and as I approach the number 1, that's this x value right here, as I approach 1 from the left-hand side, what does it look like my graph is approaching? What y value does it look like my graph is approaching? Well, I would say as I approach 1 from the left-hand side, it looks like my y value is going to be the number 1. And then from the right-hand side, as I follow this way, just right along the graph, as I approach 1, this line right here, as I approach this from the right-hand side, what does it look like my y value is going to be? Well, it looks like my y value is going to be 2. Those don't match, and so we write for our general limit that this is d and e, does not exist. Last but not least, you can always find your value of your function at a particular point. So these were limits, that's just getting infinitely close to 1. Actually, at 1, where is my closed circle, or where do I have a dot on my graph? And it would look like the actual dot or the closed circle is right here. So just making that different color. So that's where the actual dot is. So I would say that f of 1 equals 2. All right, let's go ahead and we'll try another example. So now I'm again doing 1, and I'm doing it from the left-hand side, right-hand side, general, and then I'll find my actual function at 1. So as I approach 1 from the left-hand side, I'm just following my graph, and I'm approaching 1 from the left-hand side. Well, my left-hand limit looks like it's going to be -1, right? Because that looks like approximately, might be a little more. From the right-hand side, follow my graph, it looks like my right-hand limit would be +1. My left-hand limit and my right-hand limit do not match, so this is going to be d and e. And then where do I have my actual point on this graph? Well, my actual point occurs right here, and what's the y value right there? Well, we'd say that y value is 0. All right, let's go ahead and we'll get some more examples in here. In example 3, left-hand limit as I approach 1, so I'm just following my graph and I'm getting closer and closer to my x value of 1. What looks like my left-hand limit, my y value, it seems to be approaching is 1. From the right-hand side, so I'm following my graph coming in from the right-hand side. Well, it looks like my right-hand limit is also 1. So now we have our first example of where, because my left-hand limit and right-hand limit are the same, my general limit would be 1. And then my actual function, so f of 1, do I have a closed circle anywhere on here? I would say no. So we would say f of 1, you can write does not exist if you would like. That would be fine. It also, for actual functions, you can write undefined. So there's no point that's defined for that function. For limits, we always use d and e, but for if you're just finding f of 1, so the function at 1, you can write undefined as well. All right, this graph looks very similar. So as I approach 1 from the left-hand side, it looks like my y value is going to be 1. As I approach 1 from the right-hand side, it looks like my y value is going to be 1. And as therefore my general limit is also 1 because it matches. And then now this one actually does have a point. There is actually a point on this graph. It's down here at -2, and although it's a little bit of a funky graph, that's perfectly fine. So my actual function at 1 is -2. All right, we got 4 more examples here, I believe, before we move on to some slightly new concepts. So let's go ahead and try these ones. This time we're approaching 0, so I'm looking at my x value of 0, which is right down the middle here. So as I approach 0 from the left-hand side, I'm just following my graph, following my graph well, hopefully, and it looks like my y value is 1. From the right-hand side, following my graph, looks like it's going to be a y value of 1, so my general limit exists and is 1. And then f of 0, there isn't an open circle here, and even though it isn't really defined super well on this graph because there aren't specific individual points everywhere, there is a point right there technically, right? And so then I would say that my actual function now at that point is also 1. So f of 0 is 1. Those all match, and those are all nice and neat. All right here, real quick before we do this example, go ahead and you're going to want to draw, this is supposed to be an asymptote or a dotted line, so whatever you need to do. It might already be that way on your guided notes, but this is supposed to be a dotted line that your graph approaches but never touches. Okay. So as we approach 2 from the left-hand side, this one's a little bit interesting because as I approach 2 from the left-hand side, it looks like my graph is growing, and it's just going to keep going up for forever. And so how we say up forever in y values is we say it approaches infinity. So you're going to get really good at drawing those infinity symbols. So as I approach 2 from the left-hand side, it just seemed to go up for forever. So we would say that it approaches infinity. From the right-hand side, it looks like it goes down forever, so we would say that that's negative infinity. And because those don't match, and technically infinity doesn't exist, infinity isn't a number, but if these matched, I could use a positive or a negative infinity here, whatever the matching set was, but because they don't match, I still have to write D and E. And then f of 2, notice this is a dotted asymptote. There's no points on that line, so we would say that this is also D and E. This does not exist or is undefined for the actual function. All right, wonderful. Let's go ahead and we'll do these last 2 examples, and then we'll break before we talk about limits approaching infinity. So in this example, again, this is supposed to be a dotted line. The printer or the PDF just doesn't like to do it for me. So on either of those, it's supposed to be a dotted line. So it's a graph, a line your graph, approaches but never touches. All right, so in example 7, now I'm approaching -2, which is where my asymptote is. So as I approach -2 from the left-hand side, I'm just following my graph. And as I get closer and closer to -2 from the left-hand side, my graph seems to go up for forever. So we would say it goes up to infinity. From the right-hand side, we do the same thing, just kind of follow it up. So we get up for forever, so that's also positive infinity. And again, technically, infinity does not exist, like you would never be able to hit infinity, but because these now match, as opposed to in this previous example, I can put infinity here. All right, so that would mean our general limit goes to infinity. And then f of -2, looking on this asymptote, there are no points, so we would say that this is D and E, does not exist, or is undefined. Okay. And then in example 8, again, very similar graph, but the only difference is going to be this dot here. So as I approach -2 from the left-hand side, I seem to go up for forever, infinity. From the right-hand side, up for forever, infinity. And then my general limit could also be infinity because these match. But now I actually have a point right there, right? There's my actual value. F of -2, what's the y value there? Well, the y value there is 0. Lovely. All right, so let's break before we talk about the concept of limits as x approaches infinity.